So how is pattern recognition accomplished? Well, there are different theories about it. One of the things you're going to love about cognitive psychology is that there are multiple theories about just about everything. And each theory explains part of the phenomenon, but not all of it. And so all of the theories are sort of still viable. So the template theory says that we actually hold literal copies of our experiences in our short-term memory. So, the word template is verbatim stored in your memory, for example. I used the slides that look like they have water droplets on them, right? You have stored in your memory, experiences involving water droplets so that when you see these slides, you know right off what those are. There's no thinking because you already have a template for water droplets in your memory. So when you encounter a new pattern, according to this theory, you will search through the templates that you have stored in your long-term memory looking for a match. If you find a match, then you're going to recognize the stimulus. You're going to say, oh, I know what that is. The problem with this theory, one is that if you were honestly searching through a bunch of templates, this would be really super time consuming. I mean, you would never get done because how many templates must you have stored to represent all the things you've ever experienced in the world? Like that's a lot of information. And how is it organized? And how would you effectively search it? And I mean, there are a lot of problems with that. It would just, you'd be searching for templates all the time. A good example of how time consuming it could be is the process of identifying people by their fingerprints. There are these little details that help to make fingerprints look unique, right? And a bunch of them are labeled here, things that can make one person's fingerprint look different from another person's fingerprint. So let's say that you're a person who's going to be identifying a fingerprint. So first, a fingerprint has been provided to you. So we'll call that the input. And so you have to look for segmentation within the fingerprint. You have to look at whether you think that this is the, how do I phrase this? So, because usually I just hold my finger up in class and people know what I'm talking about. So in this image that you're looking at the left side of the fingerprint, is the tip of the finger up or is the tip of the finger down? That's the orientation field estimation. Like, does this look like an upright finger or is this maybe a finger that's pointing downwards? You got to go through the process of trying to enhance the details because you can see some little scratches and gaps in this fingerprint. You got to try and enhance that. Then you've got to classify the different parts of it, the ridge, like blah, blah, blah. Look at all the steps that you have to go through before maybe you could determine whether this particular fingerprint that you're looking at matches one that's in the database or matches the one that's in front of you. Back in the olden days, they had to actually sit there with a loop, it's called, a little device that sort of you hold in your eye and it zooms in a little bit. And they would compare this fingerprint to another one that they had on file, and they'd have to look for these major characteristics, and it's just so super time consuming. Luckily now computers can do it really quickly, but the idea that you would go through all these steps that are depicted in this diagram every time you're confronted with a stimulus, that's just, it's untenable. It just doesn't make sense. Another problem with the template theory is that patterns of things that are in fact similar to each other might not look that similar to each other. So I phrase that as patterns of like stimuli occur in many forms. Like, for example, think of shells. Not all shells look the same, right? Seashells. Some look like snail shells. Some look like oyster shells. Some look like conch shells, which are kind of like snail shells, but kind of not. There's just all these different forms of a similar stimulus. Like what template would suit the concept of shell? I mean, which one gets to be the template, right? Similarly, here we have glasses, right? Like all of these are glasses, but boy, they don't all look the same, do they? They really vary. Some have handles, some don't, some have stems, some don't, some are wide, some are narrow, some are tall, some are short. One's even a pitcher. So when you think glass, which of these templates should be the glass template. So people who defend the template theory would like to point out that we use preprocessing to simplify the stimuli. So when, for example, we are confronted with an object that can hold liquid and you could drink from, we simplify the stimulus into its basic components. And so we think about its liquid holding capacity, its size being that which would allow us to raise it to our mouths, these kinds of things. And that helps us to get into the right genre to be thinking, okay, this is probably a glass, right? And then also context can help provide clues. If someone is drinking from it, it's probably a glass, things like that. And so they would like to argue that you're not just starting from scratch and just have to search through every template that you own, and you wouldn't recognize a glass that has a handle as a glass because your template doesn't include a handle. They say, no, you would use context and other clues. To emphasize the idea that context helps to provide clues, notice that on the top row, it's clearly A, B, C, D, E, F. And on the bottom row, it's 10, 11, 12, 13, 14. But what's really fun and interesting is to note that the B and the 13 are the exact same form. Like, it's not close, they're exactly the same form. But in the context of letters, that object is interpreted as a B, and in the context of numbers, it's interpreted as a 13. So, we use context a lot, and thank goodness we do, because the world is not, formed out of perfect objects. Here's supposedly somebody's handwriting that says, my phone number is area code 604-876-1569. Please call. Again, note that like the H in phone and the B in number are exactly the same form, but it's interpreted as an H in the one context and a B in the other. The word is and then the number 15 in the phone number are exactly the same form, but we have absolutely no trouble recognizing the is as an is and the 15 as a 15. Like, we have no trouble with that because our brain recognizes that context really matters. And so, while there are some problems with template theory, I think it's probably too time consuming. There are, some shortcuts that probably our brain takes to prevent us from having to go through a completely exhaustive search of templates. We use a lot of cues to help us. Sticking under template theory and this idea of context providing clues, I wanted to talk just for a second about the moon illusion. If you ever are lucky enough to see the moon in its full phase on a clear night, going from the horizon out to the center of the sky, you'll notice the moon actually looks bigger on the horizon than it does when it's in the center of the sky. When I was in Hawaii, they told us that it's because the moon's actually closer in Hawaii, and that's why it looks so big there. That's not true. The distance between the Earth and the moon varies so little that you usually don't notice it between the equator and, the North Pole. You wouldn't really notice the change in size. What's much more important is that when the moon is on the horizon, there are all these clues to distance. So you've got, your neighbor's house and their trees and stuff like that in the foreground. And then you've got the moon behind it. And the moon looks enormous because your brain says, okay, the house is right there. And the moon is like, I don't know, 1,000,000 miles away. And which is a little bit of an exaggeration, but not a huge exaggeration. And so your brain says the moon must be really big for it to look that large next to the house. Right. And so in your head, you actually like inflate the size of the moon to sort of account for, I know it's farther away than it looks right now. And so it must be a lot bigger than what it looks like right now. And so your brain actually inflates the moon when it's on the horizon. When it's in the center of the sky, there are no context cues. And so you get to see what the moon actually looks like. Now, in case I confused you or it didn't make sense or you're not believing me that it is in fact the same size, luckily we have something really super easy that would allow you to test the hypothesis that the moon does not in fact change in size when it's on the horizon versus when it's straight up above you. And that is a nickel. Get a nickel, hold it between your forefinger and your thumb, and fully extend your arm. Don't have your elbow bent at all. If you fully extend your arm, you'll find that that nickel just obscures the moon so that you can just see a glow of it, a little bit of its light around the edges of the nickel. So do that while it's on the horizon. Do it again when it's in the center of the sky, and you can confirm for yourself that in fact it is exactly the size of a nickel, whether it's on the horizon or it's in the middle of the sky. What makes it look bigger when it's on the horizon is these context cues that make your brain think it must be way bigger for it to look this large next to this house, given how far away it really is. And so it's like a little mathematical error that your brain does. So, all right. Another example of how context provides clues comes from something called the Vunt Jastrow illusion. So that Vunt is the same Vunt that we talked about in the last chapter, Wilhelm Wundt, who, as you recall, was studying structuralism and trying to figure out the nature of consciousness. So he and a student put together this illusion where you have two arcs. They are in fact the same size, but right now the red one looks bigger, doesn't it? Hold on, now the blue one looks bigger. Red one looks bigger. Blue one looks bigger. It's not a function of which one's on top. That's just an artifact of how I designed this slide. It's not a function of which one's on top. It's the one whose long edge is next to the other one's short edge. The one whose long edge is next to the short edge will look bigger than the one whose short edge is next to the long edge. Your brain is making a little compensation for the size of the object overall when you see that the long edge is right next to that short edge. That long edge sort of seemingly elongates in your brain. The short edge sort of narrows, and then it has an impact on the entire form. It's not just affecting that edge, it's affecting the entire form. So I don't know if you trust me or not, but I created this slide with an animation. And so these shapes, nothing's happening to them. I have an animation that causes that red one to move. And then I'm hopping it back by doing the back button. And so you can sit here and watch red one bigger, red one smaller. It's just an illusion. And it has to do with your brain using context to help it to understand what the shape is, what the form is, which one's bigger, which one's smaller. Those kinds of things are relying on context. So maybe pattern recognition is sometimes conducted through the template theory, but maybe other times through an analysis by synthesis, which is a really hard thing to pronounce, by the way. So in analysis by synthesis, the idea is that we have to pull together all of the elements of the stimulus in order for us to then start the analysis. And a good example of a failure of analysis by synthesis is something called prosopagnosia. This is oftentimes called face blindness. And this is, some people are born like this. Some people are develop prosopagnosia after brain injuries. It could be a stroke or a blow to the head or other things where there's a particular region of your brain on the right side behind your right ear in the temporal lobe. There's a particular area of your brain whose job it is to recognize that the object is a face, and then whether that face is known or not, male or female, all these kinds of clues are all processed automatically by this facial recognition area of our brain. When you have damage to that area, you literally can no longer recognize faces. In a really dramatic example of prosopagnosia, you may not be able to tell a face from other objects. So it's not just that you can't recognize who the face is, but you can't recognize that it's a face. And there was a classic case described by Oliver Sacks in a book that he called The Man Who Mistook His Wife for a Hat. And he talked about this man who'd had a stroke, and nobody realized he had had a stroke. But he suddenly was doing weird things like talking to parking meters as if they were people and getting really angry at the parking meters saying, you know, don't just stare at me with that blank face, answer my question, things like that. And so his wife took him to see Oliver Sacks, and the doctor said, it's possible that you've had a stroke and that's why you're having these symptoms. And the man said, I'm not having any symptoms. I don't know what you're talking about. And he stood up to storm out of the office, and he thought he was getting his hat off of the hat rack, but he was actually holding onto his wife's head, trying to, you know, remove it from the hat rack. So he didn't even know that it was a face, let alone whose face it was. Now, in the video that we're going to run into next, you can see this woman who has prosopagnosia that causes her not to be able to recognize which face she's looking at. So go ahead and watch that video, and then we'll come back and we'll talk a little bit more about it.